Hello and welcome to the 27th lecture. So, the topic of today is antiderivatives. Okay, just briefly, what are these? So, given some function f, we want to find capital F such that capital F prime is equal to little f. So example, if we have little f is equal to x squared, we want to find a function such that when we differentiate it, we get to x squared. And that's not so hard, right? Because we have the power rule. We know that the power we have to have in order to differentiate and get down to x squared has to be power 3. Yeah? But if we differentiate x to the power 3, we're going to have 3x squared, which is not the right constant. Yeah? But we can just divide through by 3, and then it will have something that will do the job for us, right? So this thing will do the job. If we differentiate this, we will get x squared. And if we think a bit longer, we also notice that we can differentiate this plus any constant we like, and it will still give us x squared, right? So capital F is the antiderivative of little f. So it's called antiderivative because it's going in the opposite direction. So previously we've been talking about how to differentiate, take the first, take the second derivative, all the physical consequences of that. Now we're going the opposite direction. Now we start with f, and we want to find something which, when we differentiate, gives us f. Right? So it's the antiderivative. And this is the start of a part of calculus which is called integral calculus. So up to now we've been doing something called differential calculus, which is the calculus of differentiating functions. And it's been quite an involved, lengthy story so far. And at this point, it will seem like we're disjointedly starting a different topic. We're going to be talking about integral calculus, which seems like it's completely about a different thing. Integral calculus, well, integration is a way to sum quantities over an infinite collection of. Let me say that again. Integration is a way to sum an infinite collection of quantities. In fact, it's a way to sum a collection of quantities that are uncountably infinite, that we parameterize by every number from, say, 0 to 1, okay? Which might sound somewhat weird, but there are actually there are many kinds of infinities, but there are two main kinds of infinities for our purpose. There is countable infinity. Infinity we can list like 1, 2, 3, 4, 5, 6, all the way to infinity. And there's uncountable infinity, which is every number between 0 and 1 is uncountable infinity. Integration is a more sophisticated way of addition. It's a way of adding things that allows us to add an uncountable infinity of different things in a meaningful and precise way. And it seems like it is completely unrelated to differentiation, but it's actually intimately connected to differentiation, and that's the fundamental theorem of calculus. So these two different sides of calculus will be connected together via the fundamental theorem of calculus. And the fundamental theorem itself is an incredibly deep and powerful theorem, but also a very simple one. Also one which is rather easy, rather natural, follows very straightforwardly from just a couple of pitches. So deep ideas don't necessarily have to be very complicated, and fundamental theorem is one of them. Okay, but that's all going forward. The main point to take away right now is that it looks like we're going to be shifting. It's going to feel like we're shifting the game, and we're talking about completely different things, but we will see that it connects all up somewhere in a couple of weeks. Okay, so the start of this new game, the start of this different side of calculus, integral calculus, is now with this thing, antiderivatives, because we'll find that being able to find the antiderivative of functions is really important for us. We're going to spend many classes learning many techniques to find antiderivatives, and this is kind of a warm-up to that. We're going to learn some we're just going to learn what antiderivatives are, and we're going to try and find antiderivatives just by not using our knowledge of differentiation, just by essentially guessing them. And it turns out that for many simple functions, we can just guess the antiderivative. And that's what we're going to be doing just now in these next few examples. So let's do this one. Let's do examples. Yeah, let's put it here. Example 1. Find the antiderivative. So I'm going to abbreviate antiderivative to anti-d from now on of the following functions. The first function is sine of x. The second function is 1 over x. And the third function is x to the n, where n is not equal to -1. Okay. Solution. So we just ask ourselves, what do we differentiate to get sine of x? And hopefully it's not going to take you long to realize that if we let f of x be minus cosine of x, that will do the job. But we want to have the most general expression, and so we're going to add c for some unknown constant. The constant could be any number that we like. Yeah? So that is for A. Now for B. Okay, so you probably remember that the derivative of log is 1 over x, but log is only defined for positive numbers, right? And this is 1 over x is defined for any number. And hopefully what is also somewhat in your memory is that if we differentiate log of absolute value of x, it actually gives this, right? So this guy is log of absolute value of x, okay? Look back in your notes, look back on these videos to see that we've given an explanation why this is actually equal, the derivative of this equal to this for any non-zero x, of course, plus c. Okay, c. All right, so we know that the power has to be x to the n plus 1, because in order to differentiate and get the power n, then we're going to have a power n plus 1, because when you differentiate, we take 1 off the power by the power rule. But if we have x to the n plus 1, we're going to have, when we differentiate, just n plus 1 x to the n, which is the wrong constant. So we're going to divide through by the constant that we don't want, which is n plus 1. And then we're going to find that this thing, when we differentiate it, does exactly what we want. It gives us x to the n. And again, we can just add c. So just basically guessing, we can easily come up with the antiderivative of some simple functions. Not too difficult. Let's do a slightly trickier example. Example 2. Find all the functions g such that g prime is equal to 4 sine of x plus 5x to the 5 minus square root of x over x. Okay, so solution. Well, this part is okay, right? Because we know the antiderivative of sine is minus cosine. So to get this 4 sine of x, we just need to have minus 4 cosine of x. And we'll differentiate that to get this thing. So it's this guy that gives us some pause. We have to think about this a little bit. But hopefully not too much, because if we look more closely, look at this. We have 5x to the 5 square root of x over x. And we just break it up. So we have 5x to the 5 over x. minus square root of x over x. And then we'll have some cancellation. So there's x to the 5, and underneath it we have x. We're just going to have x to the 4 from this. So we're going to have 5x to the 4. And then here we have x to the half, and then underneath it we have x. So that's like x to the half times x to the minus 1. So that's just going to be minus x to the 1 over 2. Yeah? And then that is way easier because these are just powers of x, and we're just summing them. Yeah? So let's see what we come up with that we can differentiate to get this thing. Well, if we differentiate x to the power 5, we get this. And we know that the power we need to... oh, I've done this wrong. This is minus. Right? This is minus. We know that the power we need to get this power will have to be x to the half. Right? But we have a constant of minus 1 in front. And if we just differentiate x to the power a half, we have a half x to the minus a half. It's the wrong power, right? Sorry, it's the wrong constant. So if we just multiply by minus 2 and then put x to the half like this, if we differentiate this, we have minus 2 times a half x to the minus a half, which is exactly what we want. Yeah. So this thing gives us 5x to the 4 minus x to the minus 1 over 2, and that's what we want. Okay, so we can do this. You know, the g of x will be minus 4 cosine of x, and then this thing that we just worked out, plus 5x to the 4 minus, plus x to the 5 minus 2x to the 1 over 2 plus constant c. The good thing about this topic is that once we come up with the answer, we can just check it by differentiating, right? So if we just quickly differentiate this thing, now becomes 4 cosine of x, that's good. This thing becomes 5x to the power 4, that's good. And this thing becomes minus 1 x to the minus a half, which is exactly what we want. That's good, and constant c just vanishes, so this is the correct answer. Yeah, so on the multiple choice, it's impossible to get this wrong if you double check. Right? There's no way you can get the wrong answer and then differentiate it and not detect it. You'll have to make two simultaneous errors that verify each other. It's just not going to happen. So you can really nail down all these multiple choice questions when they're antiderivatives because you have a way to check it, right? You have a way to check that you've done it right. Okay, good. So final thing to know about this, they are trying to mess with you. They're trying to trick you here by putting this in the kind of form of a quotient. But this isn't a real quotient. After you do some algebra, you have something like this. So this is a common thing that examiners will try and do. They'll try and make something which is not hard look hard by just putting it in some complicated looking form. So a good lesson is to not start to apply tools or use algorithms or anything before you've looked somewhat closely at this and seen that there isn't any obvious thing, to just make it an easier expression to understand. Okay, so that is example 2. Let's do example 3. This time it's find f, where f prime of x is equal to e to the x plus 2 over 1 plus x squared, and it gives us some extra information that f of 0 is equal to minus 2. Okay. Solution. All right, so same thing. We're going to find the antiderivative of this part and then this part. So the antiderivative of e to the x is easy because we know when we differentiate e to the x, we get e to the x. So the antiderivative itself is e to the x. Nothing to be too concerned about there. The next part is something we have to think about. The 2, we don't care. Let's just pull it out. So we're going to think about 1 over 1 plus x squared. And what can we differentiate 1 over 1 plus x squared? Hopefully, it'll ultimately come to you that if we differentiate arctan, we get 1 over 1 plus x squared. And that gives us the first part of what we need, because we therefore know that this thing is equal to e to the x plus 2 arctan of x plus constant c. Yeah? But we also know that f of 0 is 2, so we can further analyze this. Because if we put f of 0 into this, put 0 through this, we're going to have e to the 0, which is just 1. Arctan of 0 is kind of 0, so it's 2 times 0 plus constant c, and it's equal to minus 2. Yeah? This is 0, this thing is 1, so this implies that c is equal to minus 3. Let's write that better. And then we have the whole thing, right? So f of x is e to the x plus 2 arctan of x, and then minus 3. And then we can check that when we differentiate it, we get what we need. We can also check that when we stick in x equals 0, we do indeed get minus 2. So this is definitely the correct answer, and we are very happy. Okay, cool. Not too difficult. Let's do another one. So we're going to gradually add to the complexity of these questions, and then we're going to start to connect it to real physical problems. So let's change color, and let's look at this guy right here. Example 4, we have that the second derivative is equal to 12 x squared plus 6x minus 4. And we have that f of 0 is equal to 4, and f of 1 is equal to 1. And of course our job is to find f. All right, solution. Okay, so we have the second derivative, so we need to go from the second derivative up to f, so we're going to have to find the antiderivative twice. Huh? So let's do it the first time. So f prime of x, what do we differentiate to get this thing? Well, we see that the power has to be 3, but if we have power 3 and we differentiate, we have 3x squared, which is not what we want because we have a 12 there. So what if we do this? 4x to the 3. When we differentiate this, the 3 comes down, 3 times 4 is 12, and then we have x to the power 2, so that gives us that part. We're happy. Now let's do this, 3x squared, same thing. That thing will definitely give us what we want. That's a very bad x. I want to do a better x. Let's do that again. Okay. It's possible to be overly perfectionistic about these things. Huh? Let's do this one finally correctly. X squared. Okay. If we differentiate 3x squared, we definitely get that thing. If we do this, then sure enough, we get minus 4, and we have constant c. Now, this constant c stuff, I seem is a bit like fussy to you, but we'll later see it's actually crucially important. It really means stuff. It's not just details. So that is the first derivative. We'd like to actually know something about constant c. We don't have anything here that's going to help us, because what we would need to do is to know some specific value of f prime at some particular x, and we don't from this. We don't know any specific, for any specific value of f. Start again. For any specific x, we don't know what f prime of x is. There just isn't enough information. So there's nothing we can do to analyze what c is. So we're just going to have to keep it in this calculation and move forward. So we're going to go from the derivative to the actual function, taking the antiderivative. So this thing, if we have x to the 4, we differentiate, we get this. That's all good. If we have x to the 3, we differentiate, we get this, that's great. If we have minus 2x squared, we differentiate, we get this, we're happy. If we have c of x, we differentiate, we get c. And now we're going to introduce another constant, but we'll not call it c because we use c, we're going to call it d. Do not use the same letter twice when it means different things. Huh? So if you use c, then the next one has to be d. Do not use c again. You'll just get nonsensical answers. Okay? It's a constant here, and this guy is going to be a different constant. So give it a different letter. Okay, cool. Now we have the most general form, but now we can hope to try and find c and d because we have these pieces of information. So if we just stick in 0 into this, we have that 4 equals f of 0. And then all of that stuff cancels, and we just have d. So it just directly tells us what d is. Yeah? Good. So that's what d is. Let's save board space by just erasing this. Let's just erase this and put 4. And then if we put in 1 into this, what happens? We have f of 1. We have 1 plus 1 minus 2, which is 0, plus c. So we're just going to have c plus 4. And that will be equal to 1. So this implies that c is equal to minus 3. So now we have the actual complete answer. X to the 3, oops, x to the 4. That's x to the 3 minus 2x squared. We just found out this was minus 3x plus 4, and that's our thing. That is our function. If we differentiate this twice, we can check it's going to get to be this thing. And if we stick in 0 into this, we for sure get 4. And if we stick in 1 into this, for sure we get 1. That's it. We're all set. So this thing is the answer. We are absolutely sure. Cool. Okay, good. So we can do these things. Next picture, or the next question requires a picture. So we're going to have to erase the board to provide it. But before we go there, let me just state a very small theorem. So theorem. If capital F is the antiderivative of little f, then capital F plus c is also. The antiderivative also, let me do this better, is an antiderivative. Very much better English is an antiderivative. And that should be fairly straightforward, right? Because if capital F is an antiderivative of little f, so that means differentiate capital F, we get little f, then if we differentiate capital F plus some constant, because when we differentiate a constant it's just 0, that's still an antiderivative of little f. So we've been using this implicitly without saying it, but now we say it. It's a fact. It's simply true, and yeah, and now we've said it explicitly. Okay, I'm gonna erase the board, and then we'll do another exercise. Okay. Now we have this exercise. So, example. Make a rough sketch of f where capital F of 0 is equal to 2, and capital F is the antiderivative of little f. And the graph of little f looks like the following. One, 2, 3, 4, 5, and it looks like this. Goes up like this, it reaches some high point at 2, it comes down, it reaches some low point at 4, starts to come up again, doing something like this. Okay? So this is the graph of little f, okay? And since little f is capital F prime, this is the graph of capital F prime, yeah? And what we want to do is to sketch the graph of capital F prime, sorry, of capital F. And all we know to begin with is that capital F at 0 is here at 2. So this is where we start. Okay, the best thing to do is for you people who are watching the video is to press pause and then try and sketch this for yourself, and once you've done it, press play and then see what I do and see how close what you get is to what I actually do. Okay, so let me do this. So we know that that this thing is graph of little f, which is the same as the graph of capital F prime. We're trying to sketch what capital F prime is, and we know that oh god, start again. We know that this thing is the graph of capital F prime, and we're trying to sketch capital F, and we know that capital F at 0 is equal to 2. So this here is 2. Yeah. So since it's the graph of capital F prime, we know that initially the derivative is negative, right? And then as we go along, it is less and less negative until it hits 1, and then it is 0, and then it starts to be positive. So we start from 2, and since the derivative is negative, we have a decreasing function. It's decreasing, but it's decreasing less and less quickly because the slope is being less and less negative until we get to say something like here, and then the slope has to be 0. Yeah? So just to emphasize, this is the graph of f. Yeah? And then from 1 up to 2, the slope goes from 0 to being more and more positive, and it's the most positive here at 2. So we have a more and more positive slope. Slope is increasing, increasing, increasing with the steepest slope. Don't make it too steep. With the steepest slope occurring here at 2. And then from 2 to 3, the slope is still positive, but now it's decreasing. So it's still growing, this function, but the slope is less and less positive until when we reach 3, the slope is actually 0 right here. So let's try and lock in some of these things. Okay. So slope is 0 here. And from 3 to 4, we have now the slope is 0 and then gets more and more negative. And the most negative it is at 4. So we are decreasing, 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 decreasing like this with the steepest negative slope. And now it continues to have a negative slope, but it's not as negative. So we're still going down, but with less dramatically. Something more like this. This is the graph of f, and this is the graph of, oh, different color. And this is the graph of little f, which is the same as f prime. So we can go from the graph of f prime to the graph of f through this kind of reasoning. Cool. All right. Let's do another example. Let's talk about linear motion. So, so linear motion is the motion of something that moves exactly on a straight line, right? So if we have something that lives exactly on a straight line, then it can go forwards and backwards, but it's always going in a straight line. And in particular, we can describe its position with just a function. Let's say s of t, right? Because it's only living on this line. And what's cool about that is that we can also describe its velocity with a function, which will be the derivative of s of t, which will be v of t. Yeah? We can describe its acceleration, which will be the derivative of its velocity, because velocity is the rate of change of position, and acceleration is the rate of change of velocity. Yeah? So that's what linear motion is, and it's very convenient model kind of situation to understand things. So here is a model, or here is a question. A particle, well actually let's call it a car. So a car is moving on a straight line, and has acceleration given by a of t, which is equal to 6t plus 4. And we know its initial velocity is minus 6, and we know its initial position is 9. Okay, and then it says find its position function. Okay, let's try and visualize this a little bit. So we have the real line. Say this here is 0. We start off at 9 here. This is 9, and we have a car. Okay. And it has an initial velocity of minus 6. So its initial velocity is moving backwards at a rate of minus 6. But it also has an acceleration, and we control the acceleration, or the acceleration is given to us. And the acceleration is pushing us forward. So let's imagine that we have rockets attached to this car, which are firing. And at time 0, they are instantaneously firing with producing a force of 4, right? And therefore an acceleration of 4, pretending that the mass is equal to 1. Yeah? And then as time increases, these rockets fire more and more, and they add to the force, and therefore the acceleration increases. Yeah? So we have this car at position 9. It's got velocity going in this direction, okay? And then at that instant in time, these rockets are firing, pushing in that direction with greater and greater force. So what do we expect to happen? We expect that the acceleration produced by the rockets will gradually slow the velocity going backwards of the car until it brings it to a stop, and then it'll start to push it forwards, and it'll push it forwards with faster and faster speed. Yeah? So that's what we expect to happen, right? And what is really cool is that with our tools, we're going to actually be able to say exactly what's going to happen to this car, not just roughly it's going to go backwards and then stop and go forward. We're going to know exactly what it does at every moment in time. Okay, and let's see how that goes. So this is our acceleration. We want to go from the acceleration to the velocity. Yeah? So we know, again, the acceleration is rate of change of velocity. Therefore, the velocity is the antiderivative of the acceleration. So we are going to find the antiderivative of this function to get the velocity, and we have that v of t is equal to, what do we need? We need to have 3 3t squared plus 4t plus some constant c. Yeah? But we actually have the velocity at 0, right? So v of 0 is equal to minus 6. When we put 0 into this, it's also just equal to c, so that gives us what c is. So this implies that v of t is equal to 3t squared plus 4t minus 6, and that's the explicit, complete description of the velocity. Cool, but we want the position function, so well, actually, before we do that, let's just make sure that we find this a plausible answer. So we believe that the velocity which is initially at minus 6, will be less and less negative until it actually hits 0, and then it'll start to increase. And that's what we see here, because when t equals 0, it's minus 6, and as t increases, we can see that these positive numbers here will gradually get bigger and get bigger than 6. When they are exactly 6, it'll just have velocity 0, and then they'll continue to get bigger until it's pushing the velocity, is making the velocity get arbitrarily big as time goes forward. So this is a reasonable answer. We believe it fits with this rough understanding we have just from thinking about it. Okay, now from the velocity, now let's go and understand the position. So again, the velocity is the rate of change of position, right? So to go from the velocity to position, we have to take the antiderivative. So we take the antiderivative of this thing. We have that s of t, the position function. We need t to the 3 to differentiate to get this term. We need 2t squared. Differentiate to get this term, we need minus 6t to get this term. And then let's call the next constant d. But we also know that 9 is equal to s of 0, which is equal to d, because all these other things cancel. So we have the complete description of this thing. T to the power 3 plus 2t squared minus 6t and plus 9. In a quick reality check, that looks like the right thing because it starts off at 9 as expected. And for very small t, this thing is a lot smaller than this minus 6t, so initially it is moving backwards, but as t increases, these guys here will gradually get bigger than this thing, so then it'll start to go forwards and ultimately go forwards faster and faster, more and more in that direction as t increases. Okay, cool. Now, this is rather simple to do. I mean, calculating antiderivatives isn't a particularly difficult thing, particularly if we just have polynomials. But this is something with real impact. So I was watching a Netflix documentary series about Scott Kelly, which is an American astronaut who spent a year in space at the space station. He actually wrote a really very interesting and nice book called Endurance about this, about his life and about this 1 year in space he spent. And this was reminding me of the triumphs of the space program carried out by various countries, the US and Russia principally. And the space program is itself a rather striking example of the power of calculus. Because what is this? This is some little example where we have initial condition and initial velocity, initial position, and we know what the acceleration is, and then we know everything from that point onwards. And what is happening when we are launching rockets into space? What happened when we launched the first Apollo mission to the moon? Back in those days, 1960s, they had very basic computers compared to now. But what did they do? They designed the rocket, which is just this big, massive kind of just a rocket. It's just filled with fuel, either solid or liquid fuel, right? And on the top sits some smaller sub-rockets, and on the top of that, some astronauts, and they fire it, right? They just fire it. And then they have to somehow get this thing where various rocket stages drop off in the process. They have to get this all the way to a completely different orbiting thing. I don't have to get it all the way to the moon and then gently drop a moon lander onto the surface of the moon and be able to blast it off again, reconnect with the return vehicle and return all the way. And the reason they were able to do this is because they were able to calculate exactly what was going to happen using stuff like this. So it's not the case that somebody was steering these rockets, right? There wasn't some guy sitting on top with a wheel going, oh, a bit this way and a bit that way. They calculated exactly how much thrust they had, how much acceleration you would have from shooting off the first stages of the rocket, what speed that would send you off on, what trajectory, and then next stages where that would take you. And at various small bits of this stage of this journey, they needed the astronauts to actually control it and guide it and send it in a more refined, correct path. But mostly it was calculating the path based on knowing your initial velocity, which was 0, your initial position, which was whatever, Cape Canaveral, and your initial acceleration, and your acceleration as you continue going forward, which you know exactly because you know how much rocket fuel you put in your rocket and you know how much thrust it produces. The physics of all of this stuff is classical physics. It's physics of the 19th century. It's thermodynamics, it's Newtonian mechanics, right? The physics of the 20th century is the physics of quantum theory of very, very small things. And it's the physics of very large things. It's astrophysics, it's relativity. There is a little bit of relativity necessary to connect things up in space because these are at large scales, but not much. Most of this physics is classical physics. And the actual triumph is a triumph of engineering, of building these machines that are not going to blow apart, and a triumph of mathematics, being able to correctly calculate what would be needed to send this huge tower, this huge skyscraper of a rocket into space and send people off to some different destination and then bring them back and then land them back on Earth. And they're able to do that because of things a bit like this. What we have here is initial conditions. We know what the acceleration is, and then we know everything else about the path. But this is obviously a very simple example. This is a one-dimensional thing moving up and down. In the real problem of launching people to the moon or launching people to the space station, it's in 3 variables. It's multivariable calculus. There's more than one thing in play. There's more than just the gravity of the Earth. If you launch something in towards the moon, you have to deal with the gravity of the moon, and it becomes a more complicated calculation, but it is still a calculation of multivariable calculus, and we can do it and get it right because we have this kind of stuff, because we can exactly do these things. We have the predictive power to do these things. Imagine if we tried to send people to the moon without any of this stuff. Well, what would we do? We'd build a huge rocket and we'd fire it and go, okay, well, that one didn't reach. Maybe we need to make a bigger one. And then we fire another one, and this one just goes flying past the moon and goes, okay, now a bit of a smaller one. If we were just working with experimental science, with experimental techniques without any predictive capacity to know what's going to happen when we build these things, there's no way that would have worked, right? We would never have been able to afford the investment of just having like 10,000 trials of trying to send something to the moon and killing however many people along the process. But we were able to do it and get it right the first time because of the predictive power of being able to solve things like this with the mathematics and with the basic physical laws of Newtonian mechanics and thermodynamics that tells you how much thrust, whatever amount of liquid fuel your rocket has, and stuff like this. But we are doing math, and in particular, what I want to point out is that the math means that you can tell exactly what's going to happen from your initial conditions from this kind of stuff. So this seems kind of routine, kind of easy exercise for us, but it's a little hint of the power of the machine that we are starting to learn about. And that's the reason why most of you engineers are learning this, is that if you want to use laws of physics to build stuff and not just waste your time doing 10 million false experiments and have a good idea what's going to happen from the thing you build, then being able to calculate it, what's going to happen, is essential. And it's from stuff like this. It's more sophisticated than this, but it's in spirit very similar. Cool. Cool. All right. Let's do another physically inspired example. Example 7. A ball is thrown upwards with a speed of 48 feet per second from the edge of a cliff which is 432 feet high. When does it reach maximum height? And when does it hit the ground? Okay, solution. Let's draw a picture. So this is a cliff, 432 feet high. And this is our ball, which is thrown upwards with a speed of 48 feet per second. Oh. Okay, and we are imagining an idealized thrown ball, so it's going straight up and it's going straight down, so it's doing linear motion. Okay, cool. So, similar kind of game to before. This is something we can figure out because we have the ability to go from this initial condition and the force acting on it and then figure everything else out about it. The force acting on it is just gravity. And near the surface of the planet, we can assume with very small error that gravity is essentially constant, and gravity is producing a force going downwards at 32 feet per second. And this is something back from the lecture back on tangents when we talked about Galileo dropping his stone. So we know that the acceleration will be minus 32 because upwards is this direction and gravity is pulling us downwards. So acceleration is minus 32. Okay, and then we go from acceleration to velocity just as we did before. So velocity is minus 32t plus constant c. We know the initial velocity is given here. It's 48. So when you put t equals 0, this thing vanishes. We find c is 48. So I'll do this a little bit faster. So this thing is minus 32t plus 48. Yeah, all I've done is solve for c just in the way I did before. I stick in t is equal to 0 here, and then I use the fact that I know that v of 0 is equal to 48. Yeah? Okay, so that is velocity, and then we're going to go from velocity to position. S of t, and then if we want to find the antiderivative of this, we're going to have minus 16 t squared plus 48t plus constant d, and again, we're going to stick in the initial values. S of 0 is equal to this 432 feet here, so 432, yeah? And that's also equal to, when you put t of 0 into this, it's just equal to d, so that gives us the entire function. S of t is equal to minus 16 t squared plus 48t, oops, here we go, t plus 432. Cool. And just as before, from these initial conditions, and then from this basic stuff, so in this case it's simpler because we just have this constant acceleration produced by gravity, we have an explicit, complete description of this ball, right? And this holds true for as long as the ball is in motion. When it actually hits the ground, then other physical things come in play. The force of the ground hitting against the ball is no longer, this physical model is no longer true, but it's true when the ball is still in motion. Huh? Cool. So that is that. Now let's figure out how high does it get. So if you look at the velocity, which is here, this is as we expect. When t equals 0, it's 48, and as t increases, because gravity is pushing it down, the velocity is slowing down, slowing down, slowing down. And at a certain point it stops and it starts to go directly down. Yeah? And when it stops and starts to go directly down, it's just going to go down from that point on. So the highest this ball will reach is when the velocity stops. Yeah? And it's 0. Yeah? So highest point is when v of 0, so again, when v of t is equal to 0. Yeah. And then we can solve for that, right? So what's that? That's minus 32t plus 48 is equal to 0. And therefore 32, 32t is equal to 48. T is equal to 48 over 32. Let's divide both sides by 2. So we have, top and bottom by 2. 24 over 16, let's do it again. 12 over 8, again. 6 over 4, again. 3 over 2. So this happens when t is 3 over 2. So 1.5 seconds after we throw it, it reaches its maximum height. Huh? Good. And then when does it hit the ground? Well, we have the explicit description of its motion until it hits the ground, right? So strictly speaking, if we put t equals 0, this model, strictly speaking, when this thing hits the ground, this is false. This physical model is not true. But the instant before it actually hits the ground, it is still true. Yeah. So we are going to simply try and find the t for which this thing is equal to 0. Yeah. But what we're really doing is we're finding the t for which this thing is just a little bit above the ground, where this model still holds. Right. So we're trying to find the t such that this thing is equal to, say, 0.00000001, right? Because when that's the case, it's still in motion, this is still holding true, yeah? Yeah? But if we did find the t such that s of t is equal to 0.0000000001, that t will be incredibly close to the t such that s of t is equal to 0. So it's a fair simplification to make, is simply to find the t for which s of t is equal to 0, and that t will be the t where it actually hits the ground. Okay, so let's do that. So if s of t equals 0, that's just this quadratic. That's the same as minus 16 t squared plus 48t plus 42 is equal to 0. Let's divide everything by minus 16. So that's going to be the same as t squared. I guess this is like 32. That's like 3, right? So minus 3t, and this guy is minus 27. Not because I did it in my head, just because I know, because I already did this. So that is our guy. And then this is just a quadratic, and we can just solve it. And if we just put it in the quadratic formula, we find that t is equal to plus or minus 3. No, that's wrong. Let me do that properly. It's equal to 3. Three plus or minus 3 square root of 13 over 2. Now, when we have 3 minus 3 root 13 over 2, we have a negative t, which is meaningless. We have time going forward. So the actual answer is t is equal to 3 plus root 13 over 2. And that is the instant it hits the ground. So again, we have precise predictive power from knowing the initial conditions and just this physical law, gravity, and some mathematics. Cool. So, yeah, this is the power. This is the thing that before Galileo would seem unimaginable, that we can predict exactly the future from knowing something about the present. But that's exactly what we're doing, and it seems routine to us now. But it didn't seem routine back then. It seemed unimaginable. Huh? Cool. All right. Final words about space travel and Scott Kelly's book. So we just had midterm 2 like a week ago, and in reading Scott Kelly's book, it's incredibly competitive thing to become an astronaut. And he was writing in his book about he wasn't a serious student. He wasn't taking his studies seriously. He wasn't engaged by them until he read this book, The Right Stuff, about the early astronauts. And I've forgotten who wrote The Right Stuff. It might have been Tom Wolfe. In any case, this is a classic book about early astronaut training and the early astronauts who went off on the Apollo mission. And he was completely captivated by this book and then became more engaged with his studies and started to realize he wanted to be an astronaut. So he made some efforts to take his studies more seriously and was in I think it was in community college. And he has a twin brother who also wanted to do the same thing, become an astronaut. And he was trying to turn around from being this not very successful student to being one, because he was aware he needed to do that in order to get a degree, in order to become a pilot, and then go through all these necessary things to go and become an astronaut. And one Friday he was calling his brother about traveling back to their hometown, trying to hitchhike back to their hometown to go to some party which they were invited to. And his brother said, "Well, you have your calculus midterm coming up next Tuesday. You can't go home this weekend. You have to study." And he writes in his book that he was resistant. He was going, "What, you mean I have to study the whole weekend?" And his twin brother said, "Yes, you have to study the whole weekend. You're not doing well in the course. And if you're going to do these things that you want to do, you're going to have to start doing very well in these courses. And the only way that's going to happen is if you study." And he pondered it. He thought carefully about it and was really undecided. He was really 51-50 or 51-49%. Do I stay here, study the whole weekend, and the next few days after the weekend do all these calculus exercises to prepare for the midterm, or do I go back, hitchhike, get back to my hometown and go to this party? And it was really not a clear decision to him. But ultimately he decided to study, and he did quite a lot better in this midterm. And he started to realize that when he studies and that works consistently, he can do well. And then it became something he wanted to do, and everything transformed. But he wrote in this kind of autobiography that when he thinks back to that moment, to that evening when he was thinking about, does he travel back, hitchhike back to his hometown and go to the party, or does he study, and being really undecided about it, he thinks of that moment as if remembering a moment where you're almost stepping off a cliff, where you're on the edge of a cliff, looking down, almost falling, almost just dropping off the edge of a cliff. And this is going to, when you have such a memory, it's a memory where you're like frightened, like, oh my God, I almost did something incredibly stupid. And that's how he feels about it at the time. But when he was there as a young man, for him it wasn't a clear decision. It was really 51 to 49% stay and study. And now, all those years later, having led this rich and interesting life, as a consequence of making the choice to stay, the memory of being almost decided to go home and party in his hometown is frightening to him. It's as frightening as stepping off a cliff. And I have analogous memories of making decisions, of almost not making decisions, that now seem to me to be crazy, where the obvious right decision was the one I ultimately made, but it wasn't clear to me then. It was kind of a toss-up. So if your decisions about what you should do in your course, in this course, and other courses are unclear to you, and you have some vague idea that some path will be better, but it's really not, you're not really convinced either way, you might feel very differently about it if you take this path of choosing his path and then live a life that results in all the rewards from that. You might feel very certain that would have been the right thing, and very scared of even considering doing something different. So, yeah, read the book. It's an interesting book. All right, enough for today.